Yeah. Okay. So okay. So let's start off with just an exercise. This is something that along the line of what we were doing before the break. So this is just one of those exercises from section 4.4. So it's like this: so given, it's a warm-up exercise. Given a cylinder of volume 10 centimeters cubed, express the surface area as a function of the radius of the base. Okay, so you've got a cylinder, right? You've got a cylinder, and the base is a disk, so it has some radius, and you know that the volume is 10 centimeters cubed, and they want you to express the surface area, right? The area of the surface as a function of r. Okay, just take a minute or two and see if you can do that. Okay, talk with the neighbor for a few seconds, and then we'll do it together. Okay, who would like to start us off? Right, express the surface area as a function of the radius of the base. So how do you get the surface area? How do we describe the surface area? Anybody know can anybody tell me how one would figure out the surface area of a cylinder? Anybody know? Fern, yeah. 2 pi r h, yeah. So 2 pi r, right? 2 pi r is the circumference here, right? And you multiply that by h, and that would be if basically if you cut the can open and then rolled it out, right? So that would be, right, you've got this 2 pi r. 2 pi r is the circumference of it. So you rolled out this flat part of the can, and you get h, right? And this would be the area of that piece that you roll up to make the outside of the can. What about the top and bottom? Top and bottom, pretty easy, I guess. What's the area of the top? Pi r squared, right? So you've got 2 pi r squared, right? So the total surface area is 2 pi r h plus pi r squared, right? 2 pi r h plus 2 pi r squared. Make sense? Okay, so we wanted to express this in terms of r. The thing is that we have an h here. So how do we get rid of that h? How do we express h in terms of r? Is there any relationship between h and r? Anybody get this? Anybody think? Yes.
What I did was I took the volume 10 centimeters and then set equal to pi r squared times h.
Yes, great. So we know that the volume is 10 centimeters, but the volume is pi r squared times the height, right? Pi r squared, the base, times the height is the volume, and so we have this relationship between h and r, right? H is 10 over pi r squared. Right? H is 10 over pi r squared, and so we can just put that in for h here. Right? And that gets that, we substitute that in for h, and then that does it for us, right? We get 2 pi r times h, which is 10 over pi r squared, plus 2 pi r squared. Right? And then some simplification will occur. Right? You cross out the pi's, cross out one of the r's, and you get 20 over r plus 2 pi r squared. Okay, right. So that expresses the surface area as a function of the radius. We could have gone the opposite way. We could have expressed it as a function of the height, right? We could have replaced, instead of replacing h with an expression in r, we could have expressed this r with an expression in h, right? If we wanted to go the opposite way. Yeah. Anything that's confusing about this? Anybody get stuck? Okay, so that section is on modeling. The section that we're going into today is on optimization. And you can see how the two go together, right? You have some physical situation that you model, and then you optimize it, right? You create a function describing your physical situation, and then you figure out where it's biggest or where it's smallest, right? So that's the game we're going to play, and in some sense, our ability to optimize is not as good as our ability to model, because the only things that we can optimize at this point are parabola, are quadratic functions. So it's only going to be of quadratic functions. Like I keep on saying, once you get to calculus, you develop tools that you can optimize, much more complicated things. Okay, so yeah, so we're going to be optimizing quadratic functions, finding where they're biggest or smallest. So let's think. If we have a quadratic function, if our function is ax squared plus bx plus c, then where does the max or min occur? Where does the max or min occur? Well, to do that, we'll use completing the square. So we'll use completing. the vertex occurs when x equals. Does anybody know this offhand? But just in your memory, where the vertex of a parabola like this occurs? I'll be impressed if you know it. I'd be kind of shocked if you know it. I don't know. I wouldn't know it offhand. Anybody know this? That's okay. It actually occurs at negative b over 2a. Okay. Right. So if you have some equation that looks like 5x squared plus 3x plus 1, you know that the vertex is going to occur at negative 3 over 10. And looking at it, you see that that's where the minimum is going to occur. Right, the minimum will occur there, since this is an upwards problem. Okay, why does it occur there? Well, we can work it out just using the completing the square, right? So ax squared plus bx plus c is the same thing as a times x squared plus b over ax plus c over a. Right, you factor out the a, right? And then you do completing the square on it, right? What's this going to turn into? X squared plus bax, when you do completing the square on it, turns into what? X. So?
Plus b over 2a.
Yeah, plus b over 2a quantity squared, and then of course you have to subtract off that term that you added on. Right? And then you see, right, that's where the negative, this term is going to vanish when x equals negative b over 2a. Right, so that's the vertex. Right, so you see that x equals negative b over 2a is the vertex. Okay, everybody all right with that? Any questions? Ask questions. Don't be afraid. I don't know if this is useful to you, but when I was learning Chinese in college, my Chinese teacher, who anyway, my Chinese teacher said the key to learning is shamelessness. So that's really true. That's really true. If you think about how children learn, they learn fast because they just make all these mistakes. They get corrections. They get loads of corrections, and then their brain sort of assimilates all these things and creates a sense out of it. Right. So yeah. So ask questions. Brisa first.
So when you say it's the vertex, does that mean that if you get 10 as the vertex, does that mean it's?
That's where it's centered, right? That's where the parabola is going to be centered. So at let's say that this is negative b over 2a. That's where the parabola is going to be. That's where the axis of symmetry of the parabola occurs, right? So I've drawn it downwards. It could be upwards. Who knows? But in any case, the vertex occurs at that point, and so that's where the maximum in this case, or the minimum in an upwards case would occur. Okay. Manuel.
Can you go over how the a turns into 2a in the problem?
How the a turns into what?
Into b over 2a squared.
Oh, so that's this business of, right, we have x squared plus b over x, right? And we're just going to do completing the square on it, right? So this turns into x plus b over 2a quantity squared minus b squared over 4a squared, right? Minus b over 2a quantity squared. This, remember, if you have x squared plus ax, and you're doing completing the square on it, what do you get, right? It becomes x plus a over 2 quantity squared minus a over 2 squared, right? Because this thing, remember, turns into x squared plus 2 a over 2x plus a over 2 quantity squared, right? And then right, and this is your x squared plus ax. This is your x squared plus ax, right? And then you subtract off this thing, right? So that these things cancel off, and you end up with x squared plus ax. Okay, so this is just, all we're doing is we're doing completing the squared. This term is b over a. The coefficient here is b over a, and so what we're going to get is, capital A over 2, right? This thing divided by 2. Okay. So, all of the problems in this section are going to be basically maximizing, finding the max of optimizing some quadratic equation. Okay. So we're going to use this formula over and over. Okay. So let me give you an example. So here's a simple example. So the height of some object is given as 512t minus 16t squared. So this is something that's been thrown into the air, okay, and gravity is working on it. If you notice, when you throw something into the air, right, it actually does travel in a parabola. It actually does travel in a parabola, which is kind of cool. But in any case, so like here's some object thrown into the air and it travels in this parabola, right? And the question is, find the maximum height. Find the maximum height of this object, right? So this is some parabola, right? You want to find how high up it goes. Okay. So in order to do that, we have to find where the vertex is. What time the vertex occurs. Okay. So you look at this thing. We say, okay, we've got this thing. Do you guys want to try it for 1 minute, and then we'll talk about it. Okay, talk with each other. See if you're thinking the same way. Hopefully you're thinking similarly. Okay, So when does the vertex occur? Well, we look at that thing over there, and it says, that the vertex is going to occur at when we get to negative b over 2a. Right? Everybody okay with that? Right. So the vertex occurs at that point, right? And that's 16. Right? So you know that it occurs at 16 seconds. And just as a side observation, you see that at time 0 the height is 0. Right? When t is 0, the height is 0. And you see that the highest point occurs at time 16. And so you know it's going to hit the ground at time 32 by symmetry. Right? And then the maximum height is just going to be you plug in this thing. So you just whatever h of 16. So 512 times 16 minus 16 cubed, whatever that is. What is that? Did somebody work it out?
496.
4096. Thanks. Okay, so that's the maximum. Is that okay? Anybody have questions? Anybody have questions? Yes, Frank.
So I did it very differently.
Yeah, let's hear
I
about it.
tried to complete the square, and I was confused because I pulled the negative 16 out, and then it was t squared plus 32t.
So negative 16 t squared minus 32t, right?
Or minus 32.
Right, so then you did this thing, right? And this is going to be t minus 16 quantity squared minus 256. Right? Right, so you see that, right, that the vertex is going to occur when t equals 16. Right?
I think I just didn't know how to interpret that.
Okay. So yeah, just think about this thing, right? You can think about this thing in terms of translations, right? This guy inside here, right, is the t squared function, but it's been moved over. It's slow by 16 seconds, right? So you've got the t squared function, but it's been moved over 16 units, right? This is a translation here, right? Been moved over by 16 units, and then it's been moved down by 256, right? It's been moved down by 256, so it goes down by 256, and then it gets flipped over and multiplied by 16. So it's gonna go like that. Okay. So yeah, so you can see that the vertex is at 6 when t equals 16. Yeah, that was the point of all that translation and reflection stuff that we did earlier. That these things could become more easily interpreted. Okay. Let's see. Okay, so another example, and this is related to stuff we did last time. Two numbers add to 9. What is the largest value of their product? What is the biggest product you can get by splitting 9 into two numbers and then multiplying them by each other? Okay. Give it a try. Okay, talk with each other, please. Okay, somebody want to tell me how to do it? How do you do this? Yes. What was it?
So I started off by having x plus y equal 9,
Okay.
or just any two variables equaling 9.
Okay.
And then you can set y equal to 9 minus x.
Right.
And then since you're looking for the product, you can do x times 9 minus x, which you get negative x squared plus 9x. And then you try to find the axis of symmetry for that, which I got 9/2.
9/2, right?
And then you plug that in for x.
Right.
And then you get the biggest value essentially, which is 20.25.
What does it turn out to be? 81/4. Yeah, yeah, 20.2. Right. So yeah, so we play the game of last time. We make this thing a function of one variable, right? Say, okay, the product can be expressed as a function of one variable, x times 9 minus x, which is the same thing as negative x squared plus 9x. And then you know where the vertex is, right? It's going to be at negative b over 2a, right? So that's 9/2. And so the value there is you just plug that back into your formula and you get 81/4. So that you get 9 halves times 9 minus 9 halves, which is also 9 halves. So you get 9 halves times 9 halves, right? In other words, the best place to make a product is to divide this thing in half, right? Which is kind of what you would expect, right? The biggest thing you're going to get is a square if you take x and 9 minus x to be the same thing. Another example. Suppose you have a line y equals mx plus b, and you would like to make a rectangle underneath that line. And the question is, what is the largest rectangle you can get? Right? So you can take any point, right? You could take this rectangle, you could take this rectangle, whatever. You take some point and you make a rectangle. underneath the triangle, and you'd like to know the largest, the area of the largest one. Okay, talk with the neighbor.
Yeah, that would be good.
But that's as far as we got, because that's which one was the B value.
Okay, anybody have some ideas? You have some line, y equals mx plus b. B is positive, m is clearly negative, right? And you want to find the area of some rectangle, right? And then you want to maximize, you want to find where that area would be biggest. Well, how do we find the area of this rectangle? Jane.
Y times X.
Y times x, right? So, right, if this is x, right, this length is x, this coordinate is x, right, then the height is y, right? Height is y. Right, so the area is y times x, right? And what is y?
MX plus B.
Mx plus b, right? So you know that the area as a function of x is going to be mx squared plus bx. Right? And then we play this game, the game that we've been playing, right? The vertex is going to occur at what point? When x is equal to
Negative B over 2M.
negative b over 2m, right? And so at that point, we know that the area, negative b over 2m, is going to be m times b squared over 4m squared plus b times negative b over 2m, right? In other words, we get m, oops, we don't get an m, we get b squared over 4m minus b squared over 2m, right? So we got a quarter of b squared over m minus a half of b squared over m. Right? So we get negative a quarter of b squared over m. So that would be the maximum. That would be the maximum area we get. Right. And geometrically, you see what's going on here. Can anybody see what this is? X being negative b over 2m. Anybody see what that is? Phoebe?
It's the negative b over
Yeah, but there's actually a sort of a geometric meaning to this. So like, what's this point here? What's this point here? This is when y is equal to 0. Right? If y equals 0, what's x?
Negative b over m.
Negative b over m, right? This is negative b over m. So the y-intercept is negative b over m. That negative b over 2m is just half of that, right? So what it's saying is that the best rectangle you get is halfway, is the one that you get when you go halfway, right? That is, there's going to be a symmetry, right? Right? You take the one that's in the middle. Yes, madam.
Is that also when the rectangle meets the line of y equals mx plus 2?
The line, what?
Of y equals mx plus 2, is that when you get the best rectangle? Like when the corner of the rectangle meets the line?
Well, all of our rectangles. Remember, so the problem was to look at all of the rectangles that where the corner meets the line. So for all of our rectangles, the corner is going to meet the line. And the problem was to figure out which one has the greatest area, and it turns out that the one that is kind of that satisfies this kind of symmetry is the best one. Okay. Okay. Do you guys want to do one more of those, or is that enough? That's don't mind either way. I'd say don't mind either way. That's probably enough. That's probably enough. Okay. Let's go on to the. Let's go on to the next section. So. The last two sections are a little bit different from the earlier ones. They're not about optimization. They're basically introducing you to giving you a better understanding of polynomials and rational functions. So start here. So developing an intuition for polynomials. Okay. So okay. So just some terms, right? So a polynomial, which I'll always abbreviate like this, is a function of the form, p of x equals some constant times x to some power plus some other constant and x to some other power to one less power, one less, plus all the way down to a1 x to the first power plus a0. Okay. So it's just something that looks like this, right? Where the AI are constants, and n is a natural number. Right. So this is something you know. It's just now said in formal mathematical language, right? You know what a polynomial looks like, right? Polynomial could look like 3x squared plus 3x to the fourth plus x squared plus 2, right? That's a polynomial, right? Right. And okay, and we're going to assume that an is non-zero, because otherwise, why are we even including it? Okay. So here, this would be our A4, right? This would be, so here, this would be A4, right? A3 would be 0. Right? A2 is 1, and A1 is 0, and A0 is 2. Right? These are the coefficients, right? You have this 3, 0, 1, 0, 2 in this one. Right? You guys getting this? This was really confusing to me when I first saw it. Okay. Maybe it's not. Maybe it's clear enough. Okay. So this n is called the degree. The degree of the polynomial, right? So this is a 4th degree polynomial, right? The degree of this polynomial was 4. This example, right? Right. There's another term. If it's just a single term like this, it's called a monomial. You don't really have to know that, but it's a term introduced in your book. Yes, Vivi.
I just have a question.
Yeah.
For the second term, like n minus 1, why do you have the n minus 1 there? Like, if the a's don't usually have like a relationship. Does that make sense?
Well, these are just the it's just a numbering system on the coefficients. So this is like A4, right? So like if I write this guy out, it's 3x4 plus 0, x3 plus 1, x2 plus 0, x1 plus 2, right? And so we're calling this guy A4, A3, this is A3, this is A2, this is A1, and this is A0, right? So this, the first one, if we're calling the first one A sub n, this one is going to be called A sub n minus 1, right? N is the degree, so like A4, this would be the next one is A3, and so on and so forth. So it's just a naming system, right? The coefficient on the thing to the nth power is designated A sub n. Yeah, that's it. Okay. Anybody else? Any other questions? Okay. So a bunch of rough remarks. So roughly speaking, things that look like x to the n looks like x squared if n is even, and x cubed if n is odd. And bigger than 1. Okay, so if you see something that looks like so x squared looks like this. Looks something like this, right? Oops. Does not look like that. X squared looks something like this. Okay. Right? And if you see something like that, if it's a monomial, it's probably it's going to be some power of some even power of x. It might like be x to the 4th or x to the 8th or something like that. So the ones that have, if it has like if it's x to some even power, it roughly looks like an x squared function. Okay, and then so these are the even ones, even monomials. Monomials, and then the odd monomials look like x cubed, roughly speaking. I shouldn't say that. Even powers of x. And these guys are the odd powers of x. Okay. Okay. So, if you see some function and you see that it looks, something like this, and it's a polynomial, you can guess that it's going to be that the highest power is probably is an even power. Okay. So okay. I'm just going to put out some facts about polynomials. First off, they do not jump or skip. Right? They're continuous is what we would say mathematically. That they don't have any breaks. Right? This is not a polynomial. Right? If you see it's got a break in it, it's not a polynomial. This is what's called continuity. Second, their graphs have no corners. Okay. So you never see a polynomial that looks like this. Okay. If you saw something like this, you would know it's not a polynomial. Polynomials can't have this sort of like abrupt change of direction. It's impossible for them. It's true that if you take greater powers, greater and greater even powers, then it starts sort of heading towards a corner. It starts becoming more and more corner-like, but it can never become an actual corner. 3, if the degree is n, then it has at most n minus 1 turning points.
So the graphs don't have corners?
That's right. The graphs, have no corners. Thank you. That's 1,000. Okay. And fourth, if the degree is n, when x is large, the polynomial is basically like area and x. Looks kind of like a monomial. Looks like a monomial of that greatest degree. Okay, let me stop there. We'll start off next time with sort of a game where I'll draw things and you'll say, okay, that has to be what kind of polynomial? What can you say about the polynomial from the graph, right? Okay. again, if people need to know their grades, just send me a mail and I'll give you some rough estimate. Those of you who need to take the exam today, talk with me after so we can figure out when you're going to do that.